Man, I really need to find some kind of a greeting for the beginning of my channel. Welcome back to Ox Tools, I'm Tom. Hey guys, welcome back to the shop. Welcome to another episode of NYC CNC. Hey guys, welcome back to the shop. Gentlemen, welcome back to the shop. Welcome to Turn Right Machine Works, my name is Keith. G'day, Chris here, and welcome back to ClickSpring. Hey, welcome to the next part of the video on the jeweler's lathe. Before I get started, I just thought I'd do another overview of sort of the point of this project and maybe why I'm building another tiny lathe. This project is going to be a manual lathe. I'm actually making it on all manual tools, which has been interesting. There are some things I made on the tarmac, but there are things I could have made, I guess, on manual machines. So you see it's got a dovetail bed here. I've got the spindle cartridge I made myself. I've got it connected to a brushed DC motor called a CIM motor, C-I-M, and it's a sort of a 300 watt motor that costs about $30, so it's, I guess, price per horsepower is quite good. So a normal lathe works in Z and X coordinates, and that makes it really hard to do complex curves and things. The idea behind this lathe is it's going to be sort of like a almost like a freestyle artistic-y kind of lathe. So if you want to make like a pen or jewelry or pipe stems, things like that, and those are things I've made in the past just for gifts and things, it's really hard to do that with perpendicular coordinate systems. So if you imagine moving in X and then moving in Z and then moving in X, you get a lot of sort of etch-a-sketchy marks, and that's kind of the root of the problem. If you think like an etch-a-sketch, if you only move in the two dimensions, it's really hard to do curves. Now I know CNC machines obviously can do curves with absolutely no problem, but I like working with my hands, and I don't always like doing CAD of something before I start making it. You can also do complex curves on manual machines with attachments, but at the same time, I don't want to do a drawing and sit down and think of how I'm going to machine it and then machine it all the time. Sometimes I just want to put stock in and see what happens. So I'm going to have a Z-axis, and I'm still going to have a cross slide, but the cross slide is actually going to have sort of a rotary axis on top of that, which will be similar to a ball turner kind of thing. And then I'm going to have another linear axis on top of that, kind of like a pivoting compound slide, I guess you could call it. And then on top of that, I'm going to have an additional rotary axis. So I'm going to have all these axes. And the idea is going to be that you can use the cross slide to set your radius, and then you can actually do the cutting on this second rotary axis, if that makes sense. But yeah, it's going to be it's not going to be screw operated, because obviously humans have a really hard time doing sine curves with velocity profiles with their hands. So a lot of it's going to be lever operated. So if you think about if you're familiar with the tag lathe, for example, it has a lever-operated tailstock, which is, I guess, not totally uncommon. It's good for sort of fine drilling where you want a bit of force feedback when you're feeding. But I'm going to have the entire Z-axis is going to be lever-operated. Cross-slide is going to be lever-operated, and then there's going to be sort of special levers on the rotary axes. And I think that's going to be pretty cool. I think it'll probably take some practice to learn how to do, but I think it'll be sort of a lot more organic when you're actually trying to make something off the cuff, as it were. So I haven't figured out tool holding yet. I've just left this as a 16mm shaft. I think it's 16mm. It doesn't really matter. No, it's 3/4 of an inch, sorry. So I could thread that to accept accessories. I could taper that. Whatever I do, right now it runs out about $1.50 thou, which is honestly better than I thought it would be, but I'm probably still going to grind it in. So I'm thinking, I don't know, probably some creative work holding solutions in the future, but yeah, I think it's going to be a neat little machine. A couple people have sort of asked me why I wouldn't just buy something like this. As far as I know, a machine like this doesn't really exist. And the other thing is I just like making machines, to be honest. I could have bought my own CNC lathe, and that probably would have ended up being cheaper overall. I mean, the tarmac slant bed lathe I think is like $10,000. Like it's expensive for a home gamer, but really it's not that expensive of a machine. yeah, I mean, I just like making stuff, and if there's something I don't like doing, then yeah, I'll spend money on that. Like, I can't imagine I would enjoy winding my own motors, so I buy motors. And yeah, I mean, it's something I've been sort of trying to keep track of a lot more when I'm working on stuff is do I enjoy doing this? And if I don't, why am I doing this? You know, it's sort of at the root of it, it's that I don't want to really waste my time on this planet doing things I hate, especially in my free time, so yeah. Yeah, so I mean, that's a pretty quick overview of the project, I think. This is what it sounds like when it turns on. So that doesn't sound particularly good, but I would attribute that to the fact that the motor is brushed, and those are a little louder than brushless motors. And I've also got these skateboard bearings for the idler, and the internal clearance on those is actually pretty atrocious. That's, I think, how they get such fast rolling speeds, is they just have a whole bunch of clearance in there. So they rattle around a bit. I'm probably going to get real bearings with rubber seals and maybe even put an actual idler over this, but for now it's, you know, just for test cuts and things, it works. Certainly got some torque to it anyways. Yep, so I guess let's get to the individual parts. I guess the first big update since the last video is that it's black. I would highly recommend anodizing aluminum for anything that you want to look nice. Aluminum's an incredibly soft metal, and it scratches quite easily, whereas conversely, anodizing is actually very hard. So it doesn't tend to scratch very much. It also usually hides scratch marks or imperfections fairly well when it gets done. One thing I've sort of learned to do since I've started getting my parts anodized is to wrap everything in brown paper when I'm not actively taking a photo of it for Instagram. The brown paper just protects it from like grains of sand all over the, you know, on your desk or whatever, or wherever you store your parts. So you can see I didn't anodize the spindle cartridge. It's not actually going to get exposed. You won't be able to see it. There's going to be a little cap that goes over here and sort of protects the bearing from chips and things, but next off you can see I actually added a groove back here, and I've got an idler system. So if you look in there, that's actually a slot that the nut fits in, and on the other side you see the shoulder bolt and some bearings, and you can't really see it probably, but they've got a little washer in there just to protect it. So this is probably a non-ideal implementation of a shoulder bolt. I love shoulder bolts, but because this is technically probably a reversible load, so if you imagine the belt slapping back and forth, it's going to bend this in opposing directions. And fasteners really don't like bending, so, you know, 300 years from now it might break. Next off, you can see I did my usual J-section pulleys. This is the belt. The belt number is 140J, which means it's a 14.0 inch circumference and J-section pulley. Sometimes you'll see a 6 after that, so 140J6, and that means it's got 6 grooves. This belt is actually the same belt that's used on DeWalt planers, so it's actually quite easy to find. So that sort of goes on like this, and then my super loud but cheap and powerful motor goes on in here. So like I mentioned in the last video, I actually designed this to be able to accept NEMA 23 size motors as well, if you wanted to put like a brushless DC motor on it or a servo or something. It totally crossed my mind, but I spent my ClearPath money on my 3D printer, which incidentally I am going to do a video on why I did that. I've been sort of not overwhelmed, but certainly surprised at the number of people who have been like, dude, you know that's a waste of money. It's really not. If anything, it's marginal returns. So there's definite advantages to it. Whether or not those advantages make a huge difference at the end of the day is a little bit yet to be seen. So I'm going to do probably a whole video on that. Whole video on trapezoidal motion profiles and things. And yeah, I'm probably going to do a kind of a philosophical video on why I like having nice things versus, you know, Chinesium stepper motors. So yeah, anyways. So this is probably something I could have hooped on before I tightened the motor on, but there, so that's the belt on. As you could probably determine yourself, this actually slides in the notch with the nut, so I just tightened it up like that. It is a hair loose still, a little bit looser than I was hoping. I was a little unclear if the 14-inch circumference was the sort of the pitch circumference, or if it was, you know, the outside or the inside. It's a little bit inconsistent in specs. So yeah, I mean, we're a little bit slack, but I think I'm going to put probably a sleeve over here with flanges. Good rule of thumb for belt design is that your idler shouldn't be smaller than your smallest sheave. So yeah, I mean, this is due to expand anyway, so I guess I'll probably just put something on it. Alright, so the next part that I did was the bed. This is, well, I guess this is probably more of a base than a bed. So this, the basic gist here is that this actually fits under like that. It screws in from the bottom. Now I've got this big channel around here. The idea behind that is if you're turning something like if you are in fact doing something artistic, like, you know, jewelry or something, and it's made out of silver, you want to collect your silver afterwards, so you try to catch your chips. I am happy to say I put a lot more thought into chip control in this lathe. So I've got these are stainless steel skirts, I'm calling them, and they just sort of screw on from the outside like this, and you can actually see they sit so the lip is actually over the edge of the trench here, so everything should trickle off there into there. And finally, this is going to be probably almost impossible for you to see. It's just a see-through acrylic cutout. I like to prototype in acrylic sometimes because you can hold a threaded hole, but it's still pretty cheap. So this is obviously going to be stainless steel piece eventually, but that fits in and overlaps the skirt. So you've got the coolant or the chips or whatever hitting here, and then rolling down there into the trench, and there's going to be a drainage area here. So yeah, like I said, these are stainless steel, 304. 316 is much more corrosion resistant than 304, but it's also much more expensive. So, you know, it's fine with 304 or whatever. I'm going to probably put either not a reflective finish, but certainly a shinier finish than this, maybe a brushed finish even. So that's those two pieces. Let's see. Oh, so this is the Dovetail. Incidentally, I should add that these were both manually machined, so this still remains a manual machinable project. This is made out of a stainless steel called 17-4. That's the same stainless steel as the spindle, actually. So you've got pretty good corrosion resistance, but more importantly, you've got hardenability and you've got good dimensional stability. So I could harden this if I wanted to. The mating piece is probably going to be brass, so it's not going to make a huge difference. I may not even harden it. But even if I don't harden it, I wouldn't expect this to move dimensionally. I would anticipate that it was made using hot rolling, so quite dimensionally stable. And I've got this trench down the middle. This looks for all the world like it's for a lead screw, but it's not. It's for that sort of pushing lever system, but it's also for chips to build up and get swept into. And again, that's just to control coolant, chip flow, etc. So that actually screws on right here. I am going to get this bottom part anodized too. You'll see in the machining footage I actually managed to break a tap off in it. So I used a junky end mill to get that broken tap out, but I think there's still a bit left in. And nothing makes anodizing companies angrier than having steel get in their tanks. So I'm going to have to get that out, I think. The observant among you will have noticed that there's actually no locating features on the Dovetail itself, so that's because I wanted to keep this adjustable. If you can't make something accurate, you should make it adjustable. So, you know, operating under the assumption that I didn't want to make it accurate, if I make it adjustable, I can dial it in to be whatever I want. So yeah, that's that. The bottom, you can see countersunk holes here. It's just M6 fasteners, 1/4 20, that obviously work too. These are stainless steel. I don't know if they'll stay stainless steel. They're just they're called 18-8 stainless steel, but it's actually the same steel as 304. I'm not sure why that distinction has been made. Alright, so that's where we're at right now. We've got the dovetail and the base finished. Got the skirts cut out, but these are just water jet out for now, so I've got to clean them up a bit. I've actually got the back plate cut out as well, but again, it's just water jet, so I've got to finish it up a bit.